Hello and welcome to another video lesson with Mr. Roman. Today we're going to be looking at solving systems of equations by substitution. And here at the top I just put a quick definition of what the system of equations is. And recall that a solution to a system of equations is any ordered pair that makes all of the equations true. Another way you could say that is any ordered pair that satisfies all the equations in the system is a solution. So let's take a look at the ordered pair 2, 7, and to see if it satisfies the equations here in this system. So 3x plus 2y equals 20, 4x plus 6y equals 30. So we're going to substitute 2 for x and 7 for y. And we're going to evaluate this expression down to 6 plus 14 equals 20, which does come out to be 20 equals 20. And that's a true statement. So we've passed the first test. Now let's look at the second. So we plug in the 2 and the 7 again for x and y. We start to evaluate the expression, and then we get 54 equals 30. So that's a false statement. And what this means is that the ordered pair 2, 7 is not a solution to the system of equations, because remember, it has to satisfy all the equations. But let's say we were to use a different ordered pair, for example, 6, 1, and we were to substitute that in. Now we can evaluate it. And we get a true statement here of 20 equals 20. And then using that same ordered pair in the second equation, we substitute in and we evaluate, and then we get the statement 30 equals 30. Now that is a true statement. So now that we've got two trues here, then that means that the ordered pair 6, 1 is a solution to the system of equations. Now the real question is, how do you find those ordered pairs that are solutions without having to just randomly guess? Well, we're going to use a process called substitution, and recall that there are 3 possible solution types for a system of equations. So you have type 1, which is one solution. Algebraically, that means there's one ordered pair that satisfies all the equations. And graphically, it's one point that all the lines on the graph share, or in other words, where they all intersect. The second type of solution is infinite solutions. Algebraically, that's when all the variables are eliminated and the remaining statement is true. Graphically, that's where the lines on the graph are all the same. And then the third type of solution is no solution. Algebraically, that's when all the variables are eliminated and the remaining statement is false. And then graphically, the lines are parallel, which means that they will never intersect because they have the same slope. And again, substitution is the process of replacing a variable or quantity with something that is equivalent. Now, if we look at this system of equations, in example 1, we can see that x is already isolated on the right, and we can use this 54 plus 18y to replace the x here. Since we know x is equal to all this stuff over here, then we can replace x with the 54 plus 18y. So let's take a look at that. So notice how it went inside parentheses here with the x being replaced in red, and the negative 10 that was out here is going to be multiplied to whatever's in the parentheses. Now, in order to break this stuff out of here, we've got to use what's called the distributive property. So the negative 10 is going to get multiplied to the 54, and it's going to get multiplied to the 18y. So now when we do that, we're going to get negative 540 and negative 180y. Then I can look at what are the like terms on the left side of the equation. So now I look at the like terms as negative 180y and negative 7y, which if I combine those would give me negative 187y. So now I can solve this two-step equation here by adding 540 to both sides. That's going to leave me with negative 187y equals 561. And then we can divide both sides by negative 187. And that's going to give me y is equal to negative 3. Now, that's only half of the solution. So now what we're going to do is we're going to take that y equals negative 3, and we're going to plug it in over here to the original equation for y. So doing that, we get 18 times negative 3, which is negative 54. And then negative 54 plus 54 is 0. And what we can say then is our solution is it's a type 1 solution, which is one solution, and it's the ordered pair 0, -3. So now let's look at a second example here where we have a system of equations, and we don't have the convenience of having one of the variables already isolated, but notice we could always, let's pause just for a moment there. We could always isolate the x over here so that we can use it as a substitution. So let's go ahead and take a look at that. So we're going to start by subtracting -14y. I'm subtracting 14y from both sides. And remember, there's a understood -1 in front of that x. So now we have to divide by -1 for everything, which is going to give us x equals -56 plus 14y. Now we can use that to substitute in here for the second equation for x. So notice what happens. The x gets replaced with the -56 plus 14y. So this is what happens. And then the 3 stays on the outside of the parentheses. And to break that stuff out of there, we're going to have to multiply that 3 times the -56 and times the 14y. So let's go ahead and take a look at that. We'd get -168 plus 42y. And then if I look at what my like terms are here, I can see the 42y and the -42y are like terms on the same side of the equation. And when I combine those, they go away to be 0, and I'm left with the statement -168 equals -168. Well, the variables have been eliminated, and this is a true statement. So recall that the second type of solution that we looked at, which was infinite solutions, is when all the variables are eliminated, the remaining statement is true. That means you're going to have infinite number of solutions. And let's see here. That's going to be right here. So we're here, and then we said that this is a true statement, and then that's going to mean that we have type 2 infinite number of solutions. All right, so let's look at a third example. And again, we're solving the system of equations, but we first need to isolate one of the variables, and it looks to me like the y here would be the easiest one to isolate. And we'd be doing that by subtracting 2x from both sides. That leaves me with y equals 10 minus 2x. Now I can use that to substitute for y over in this equation, and we're replacing it. You can see that the 10 minus 2x goes inside parentheses, and you've got that -3 out here that we're going to distribute here in just a moment. So we're going to take -3 times 10, and then -3 times -2x. Notice the negative times the negative here. That's very, very important. So when we actually multiply those, you get -30 and positive 6x. And then we look to see the combining of the like terms on the left side, which is the -6x and the positive 6x, which that would be 0. So now that -30 just comes down, and then the 15 just comes down. And we're left with a false statement. And what that means is that we have basically the type 3. So algebraically, when all the variables are eliminated, the remaining statement is false. That's going to mean that we have no solution. Okay, so let's take a look here. False statement, type 3, no solution. And that concludes our video lesson.